In the lower atmosphere of the Earth, there are negative and positive ions created by radioactive elements in the soil and cosmic rays from space. A certain region of atmospheric electric field strength is 120 volts per meter, directed vertically down. Due to this field, singly charged positive ions, 620 per cubic centimeter, drift downwards, and singly charged negative ions, 550 per centimeter cube, drift upwards. See figure 29-21. The measured conductivity is 2.7 times to the negative 14th per ohms meters. Calculate the ion drift speed, assumed to be the same for positive and negative ions, and the current density. All right, so the key point here is approximate. So they don't say that we're supposed to approximate, but that's exactly what we're going to do. Because first intuitive thought here is, all right, we have charged particles. You basically draw an electric field. So we have positives moving down, which means the bottom is going to be negative. And we have negative charges moving up, which means the positive is going to be at the top. And so basically then we get an electric field going downwards from the positive to the negative, which seems reasonable. And then if you have a charged particle in here, your first thought is, a charged particle, force equals QE, which equals mass times acceleration. And so we have a constant acceleration, and we can calculate it that way. But that is not what they're asking for. They're asking for a drift speed. And you're like, well, what's the speed here? It keeps accelerating because it's a constant acceleration. Kinematic equations, yes, that's true and reasonable, and in a vacuum, that is correct. In this case, this is more like a terminal velocity, and so we're going to approximate. The approximation we're going to use is, and I'm just going to cut to the chase, is current density. I know J, I probably should do a big J. I'm going to use small j. I like small j. Not important. I know, excessively confusing. My fault. Is conductivity times electric field, which is approximately the electron density times the velocity, the drift speed. So this is the approximation we're going to use. We're going to use this for both of them. So they give us the density and the electric field. And we want to find the drift speed assumed to be the same for positive and negative. Since we assume it's the same for both of them, actually we're going to find the current density first. So current density is going to be J, and it is going to be the conductivity, which is 2.7 times 10 to the negative 14th times electric field, which they tell us is at 120. And that's going to give us a small number on clear 2.7 times 10 to the negative 14 times 120. That gives us 3.24 times 10 to the negative 12, which is slow and specifically not faster than the speed of light. So therefore, may be possible. Okay, so now that we found the charge density, the current density, so it's amps per square meter. Now, and the whole meter second thing, speed of light, nope, that's wrong. Not important, irrelevant, because it's not the speed of light, it's current density. So now we're going to find the ion drift speed. So we now know what this is, the current density. We're going to set that equal to the density times speed. Therefore, the drift speed is going to be the current density, 3.24 times 10 to the negative 12th, divided by current, let's see here, the charge density. So the charge density is going to be the positives minus the negatives. So it's going to be 620 minus 550. Actually, no, it's going to be plus, because the positives moving down is creating a current going this direction, and the negatives moving up is also going to create a current going down, because a positive moving the positive direction is the same as a negative moving the negative direction. So we're actually going to add the two together because they are both, one's positive, one's a double negative. So there, and those are ions. So these are going to be electrons. I'm going to do this down here. So I'm going to say density is 620 plus 550. And I'm going to say these are electric charges per centimeters cubed. There we go. And so now we're going to have to do this, convert centimeters to cubic meters, just do SI units. And we're going to have 100, which I'm going to write as 10 squared centimeters per 1 meter. And we're going to do that 3 times so that we have cubic centimeters. And then we're going to multiply 1 by itself 3 times as well, but that's still going to be 1, so I'm going to call that good. And we want this in terms of coulombs. So I'm going to change the electric charge to coulombs, which is 1.602 times the negative 19th coulombs per elementary charge. And so putting this into a calculator, I'm going to get 620 plus 550 times, I'm going to call this 10 to the 6 because we have 10 squared 3 times, times 1.602 times 10 to the negative 19th. And that gives us an answer of 1.87 times 10 to the negative 10th. And that's going to be coulombs per cubic meter. All right. So now I'm going to go back up to here, plug that value in. Get rid of that random line. There we go. And whoop. Take it easy. There we go. So now we can say this is quantity 3.24 times 10 to the negative 12th divided by second answer. And that gives us 1.73 centimeters per second. 1.73 centimeters, and I move the decimal place over 2 per second. That is going to be the answer to part A, the ion drift speed, and then the current density we found earlier. This is going to be part B. So the key to this one is the idea of its distant approximation. And the formula we're going to use for this approximation is this right here. Current density is conductivity times electric field, which is equal to the charge density times the drift speed. So, hope that helped. See you on the next problem.